In this module, we'll be talking about the behavior of gases. So this first video will be just about the properties and movement of gases. And some of the stuff at the very beginning will be things that you are familiar with because we've used these definitions when differentiating between gases, liquids, and solids. But I promise we're going to go in a little bit more depth since we have an entire module about it. So gases, remember, are widely separated particles. And in a sample of a gas, you have a lot of free volume. What we typically measure for gases is the property of pressure. So this is a force per unit area. It's just kind of a physics reminder. Now we have units that are sort of derived units, so you're not going to see the force in there explicitly. You're not going to see the units of area in there explicitly. But just like we did with something like a joule, which you could break down into a kilogram meter squared per second squared, that's possible also with pressure units. We just happen to not need to do it for the applications that we're looking at. So the units that we will see and use a lot, these standard units, are atmospheres, which we abbreviate as ATM, and normal pressure, so just kind of wherever you are, the approximate pressure just kind of in a regular room is about 1 atmosphere. Now this is going to vary depending on where you are relative to sea level, but that approximation is for just about sea level. Some other units that we'll see, and these are all useful in different situations. We'll see things like millimeters of mercury, torr, pascals, even things like PSI, which is pounds per square inch. So this one, we'll label it as PSI, but right, that's a force per unit area. So you can kind of explicitly see that definition of pressure in pounds per square inch. Some conversions that you will need. 1 atmosphere is equal to 760 millimeters of mercury, and 1 millimeter of mercury is equal to 1 torr. So 1 atmosphere is also 760 torr. 1 atmosphere is equal to 101,325 pascals, and 1 atmosphere is equal to 14.7 pounds per square inch. We will also look at densities of gases. So we've used density to talk about solids and to talk about liquids. So it's appropriate that we also talk about densities of gases. And these are highly dependent on pressure and temperature. So you will find for solids and liquids that those densities can be dependent on pressure and temperature. You'll see some variations, but compared to the variation that you see for gases, those will be very small. So the densities of gases are typically small values, which affects the units we use. So we measure densities of gases usually in grams per liter. So when we were looking at things like solids and liquids, we were looking at grams per milliliter. So, a much smaller volume than 1 liter. So, 1,000 times smaller, if you will. You can calculate from information such as pressure and temperature and a couple other variables what the density of a gas will be. So density is equal to pressure times molar mass divided by R, which is a constant that I'm going to give to you, and temperature. So P is pressure in atmospheres. M is molar mass. It's an uppercase fancy M. And this is in grams per mole. So you can just read it off the periodic table or add it up from the periodic table. R is the gas constant. And the value of the gas constant is 0.08206 liter atmospheres divided by moles times Kelvin. So you can tell from the units of this constant that we need to use pressure in atmospheres, right? This is great. The moles are going to cancel out with that grams per mole in the molar mass. And it's giving us a look ahead. Our temperature needs to be in Kelvin. All right, so let's get a box around this. That is the equation to calculate density. I'm going to give you another equation to calculate density under very specific conditions. So there are a set of conditions called STP, which is an abbreviation for standard temperature and pressure. And STP is when the temperature is equal to 0 degrees Celsius, so 273.15 Kelvin, and the pressure is equal to 1 atmosphere. In this case, the density is equal to the molar mass, which we can get from the periodic table, divided by the molar volume. And the molar volume is 22.41 liters per mole. So we'll see this, we're going to get into the ideal gas law in the very next video. So if you have a gas that's behaving ideally, it's at 0 degrees Celsius and 1 atmosphere. Every mole of gas you have will take up exactly 22.41 liters of volume. So we can use that value under standard conditions to calculate the density. All right, so these are some properties of gases. We're going to talk about the movement of gases because we have a few words that describe different ways that gases can move. So the first word is diffusion. You've probably heard this word before, but I am going to give you an explicit definition for it. It is how a gas spreads in response to a concentration gradient. So it will move from an area of high concentration to an area of low concentration. And the rate of diffusion depends on the molar mass. So uppercase fancy M. Heavier atoms, or heavier, we'll say heavier molecules, because it could be either, move more slowly. The other way that gases move, you might not be familiar with this word, and we have the added difficulty in that it can sound a lot like diffusion. This is effusion. And effusion is how a gas escapes from a container through a small hole. So it is technically moving similarly to what's happening in diffusion, in that it's probably going from a high concentration to a low concentration. But explicitly, this effusion experiment is when you have a gas in a container and it can escape that container through a small hole it actually goes into another container so that we can measure how quickly it takes to get over there. And the reason that we do that is because we can use something called Graham's law of effusion to identify an unknown gas if we have some known information. So I'm going to say a little bit more, since we had what the rate of diffusion depended on. The rate of effusion is proportional to 1 over the square root of the molar mass. And the reason for this is going to be clear when we have a full equation. So you won't necessarily have to use this relationship, but you will see this relationship show up in the equation we are about to look at. So Graham's law of effusion. Again, we can use this to do something like identify an unknown gas. And this equation says that the rate of gas A over the rate of gas B is equal to the square root. And remember, this was proportional to 1 over the molar mass. So if I have the rate of A in the numerator on the left, the molar mass of A goes in the denominator. And if the rate of B is in the denominator, the molar mass of B goes in the numerator. Okay, this is obviously best done with an example. And this always feels like the part of the course where when you get a problem, it feels like there's barely any information in it. I promise there's enough information here for you to solve it. And hopefully once we get kind of out of this context and you're working on other problems, that will still be the case. So the problem we're going to look at says an unknown monoatomic gas diffuses at a rate (0.462 times that of N2. Identify the unknown gas. All right. So we have rate information about N2 in relation to the unknown, or the unknown in relation to N2. Since we know the formula for N2, we can calculate the molar mass for that. So we should be able to get the molar mass of the unknown gas. And then since it's monoatomic, right, this part here is really key to our ability to solve the problem. Once we find the molar mass, we just have to go look in the periodic table. All right. So we're not quite directly given rate information in a way that's easy to plug into this equation. What we're told is that the rate of the unknown gas is 0.462 times the rate of N2. So what I can do is I could divide both sides of this by N2. And if I do that, well, it will cancel out here, which is great. And then I'll have rate of the unknown over rate of N2. Now, this left side of the equation looks like the form that I need for Graham's law. And I have a number that I can plug in there, right? So it's like the unknown is A, and I have rate of the unknown over rate of N2. N2 is B. That equals 0.462. All right. The other piece that I need is the molar mass for N2. So you should be able to go to the periodic table and find that N2 is 28.02 grams per mole. So I can get most of this plugged in, right? 0.462 is equal to the square root of the molar mass of N2. Since N2 was in the denominator, on the left-hand side, its molar mass goes in the top, divided by the molar mass of the unknown. So now I've just got a little bit of algebra, right? I can square both sides, and that gets me to 0.462 equals 28.02 grams per mole. Well, 0.462 squared, can't forget that part, divided by the molar mass of the unknown. And I need to cross multiply. So the molar mass of the unknown is equal to 28.02 grams per mole divided by 0.462 squared. And assuming that I have done all of this properly, this comes out to 131 grams per mole. And since this is a monoatomic gas, all I have to do is go to the periodic table and find the element that has a molar mass at 131, and it turns out that is xenon.